stretch. So. Your last chance to enjoy with me some statistics-free math. So we talked about two groups. We talked about the symmetric group, and we talked about the general linear group and how they are tightly interplaying when we study tensors. This is a very, very useful tool in computations at places like CERN. And so the symmetric group, we talked about the irreducible representations and how to construct them. So those are the Specht modules. They were denoted pi. And then for the general linear group, we have the Schur modules. S lambda, or S pi, lambda partition. Okay. Now then for both groups, for any group, we have structure constants. So the structure constant says if you take two irreducible representations, Alice and Bob, and you take their tensor product, then Alice tensor Bob decomposes as a direct sum of irreducible representations. So the structure constant for the triple, Alice, Bob, Charlie, is the multiplicity of the irreducible representation Charlie in the tensor product of Alice and Bob. So that's true for any group. And for the general linear group, these are called the Littlewood-Richardson coefficients. So the Littlewood-Richardson coefficients, C, lambda, mu, nu, are important in mathematics because they are the structure constants for the group of invertible n by n matrices, the general linear group. For the symmetric group, we also have structure constants. They're also important. They are called the Kronecker coefficients. And they are denoted kappa. Well, I could also go lambda, mu, nu. They also depend on three partitions, but sometimes they're also written like this. They're the Kronecker coefficients. So the Littlewood-Richardson coefficients are the structure constants for the general linear group. The Kronecker coefficients are the structure constants for the symmetric group. Let's talk about the latter. So the Littlewood-Richardson coefficients, Frank Bahn can tell you all about them. I'm going to tell you now about the Kronecker coefficients for the symmetric group. So one way to describe them, they're exactly our yellow numbers. The Kronecker coefficients are important to us because they are our yellow multiplicities. So the Kronecker coefficients are the dimensions. So for example, if I have three partitions, pi 1, pi 2, pi 3, this sort of symmetric way of writing it, it's the dimension of the SD invariance in the triple tensor product, pi 1 times pi 2 times pi 3. So I guess this would be, so in this notation, this would be k, mu, nu, and then how do you call the conjugate, the flipped thing. So this is the same, let's say in English, as the multiplicity of Charlie in the tensor product of Alice and Bob. And you can compute this. I computed some of those, using proposition 6, 6, 2, 1. It's the average over the group, 1 over d factorial, the sum over all permutations and SD, chi pi 1 of sigma, chi pi 2 of sigma, and chi pi 3 of sigma, and these are the characters. So chi is the row, the corresponding row of the character table. So can be computed from the character table. Okay? So for the symmetric group on 4 letters, we had the character table yesterday. 5, Math Bob or SpongeBob, whoever gave you the character table for S5, and so on. So what you do is you look at 3 rows of the character table and you multiply them entry-wise and you average over the group. And what you get is a number. It's a non-negative integer, and that's the Kronecker coefficient. Now, it turns out that these are actually harder to compute. So these are hard to compute. The Littlewood-Richardson coefficients, they're easier to compute. So there are many algorithms and methods for computing Littlewood-Richardson coefficients, and they are comparatively easier. So they can be reduced to polyhedral calculations. I'm not saying that mathematically, there's still many open problems. So there are many open problems regarding the combinatorial interpretation and construction of Littlewood-Richardson coefficients, but the calculation is much better understood. The Kronecker coefficients are less understood, but it's an important area of research. So on the complexity side, I think there was important work of Bergieser and Ekenmeyer. It studied the complexity of calculating Kronecker coefficients, very important here in our context and also in the geometric complexity theory program. There was important work last year by Greta Panova. She was sort of one of the stars on the math tenure track job market in the US this year. So she did some important work on Kronecker coefficients, again, in connections to mathematical physics, but that's an active area of research with tons and tons of open problems. So I just played around with this, and I did it for d equals 4. So this is the first non-trivial case, this triple situation. So for d equals 4, right, so there are 125 Kronecker coefficients. And I found them to be all 0 or 1 in this small case. Why 125? Well, because 5 times 5 times 5, right? There are 5 irreducible representations corresponding to the 5 rows in my character table, and I multiply any 3 of them. I pick any 3, so I get 5 times 5 times 5 Kronecker coefficients. I found them to be all 0, 1, and I found that precisely 15 are equal to 1. Okay? So it takes a little while. Eventually these numbers get big. So eventually, they are even the same with Littlewood-Richardson coefficient. If you start with tiny partitions at the beginning, they're all 0, 1, and later you get larger numbers like 10 and beyond, and then same with the Kronecker coefficient. But in this small case, they're all 0 and 1. Okay, so with this calculation that I did, so I just made a loop over triples of rows in my character table and I multiplied it out. Okay. Now, of course, equation 654. Now we know how to decompose polynomial functions on 3-way tensors. So if you have a 3-way tensor of any format, Shanglong, and you have a polynomial of degree d in the entries of that tensor, then you should write that polynomial as a sum over pi 1, pi 2, pi 3, partitions of d, s, pi 1a, tensor s, pi 2b, tensor s, pi 3c, and then, k, pi 1, pi 2, pi 3. That's what we just learned. And if d is 4, then these are all 1 or 0. But for larger values of d, you get some bigger integers. Okay? And so here's my 15 things. So this is proposition 6628. So Landsberg also stated this in this book, but it's always very gratifying to do the calculation yourself. So that says that quartic polynomials on tensors, on triple tensors of any format, can be written as S4, 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 direct sum, S4, S31, S31. So this is shorthand notation, right? So by this I simply mean S4 of A, tensor S31 of B, tensor S31 of C. Okay? And then you go S4, S22, S22. No, only 15. Let's write them down. S11, 211, 211, blah blah. 4, 1, 1, 1, 1, 1, 1, 1, 1. S31, S31, S31 occurs. S31, S31, S22. So these are the 15 triples of partitions that occur. 3, 1, 2, 2, 2, 1, 1. 3, 1, 2, 1, 1, 2, 1, 1. 3, 1, 2, 1, 1, 1, 1, 1, 1. 2, 2, 2, 2, 2, 2, my favorite. And then 2, 2, 2, 2, 1, 1, 1, 1. 2, 2, 2, 1, 1, 2, 1, 1. And finally, the last one, 2, 1, 1, 2, 1, 1, 2, 1, 1. Okay, so that's the canonical decomposition for quartic polynomial functions on three-way tables. Now let's try that for 2 by 2 by 2 tensors. Let's apply this in a very simple case. So if the vector space dimension is very small, many of these go away. So which of these survive if A equals B equals C is just two-dimensional? Well, I claim only those survive that use at most two parts in the partition. Right? So I hope I didn't mess up, but S1111 is the exterior power. Right? So that's the fourth exterior power. But the fourth, so this is the fourth exterior power of a two-dimensional vector space C. But you know, if you have a two-dimensional vector space, the fourth exterior power is 0. Right? So the only guys that survive in this one are the ones where the partitions have at most, you know, two parts. Everything else is 0. For all other terms, my hook length content polynomial will evaluate to 0. Okay? So in particular, we know, so for example, right? This is Landsberg 827, right? So if we look at quartic polynomials on 2 by 2 by 2 tensors, then we know there's a vector space that sits inside there, that this one will occur. Right? Now S22, C2 is a one-dimensional vector space. If you think about the hook length blah blah formula, you always know these things, you always know the dimensions. So there's a one-dimensional vector space. So just by this formal analysis, we know that there's a distinguished polynomial function of degree 4 on 2 by 2 tensors that lives in this component, that has sort of the same symmetry pattern with respect to all, and it's our favorite hyperdeterminant. So from the invariant point of view, the hyperdeterminant is this tensor product of Schur modules inside the space of quartic polynomials. Right? So this is the hypodeterminant. And then, by unraveling everything I said, by doing row symmetrization, column symmetrization, by everything that Luke explained Friday a week ago, you can recover the formula for the hypodeterminant. But from an invariant point of view, this is the hypodeterminant. Now, a little bit of philosophy. What is it we want to do? We want to describe, for example, the prime ideals of G-invariant subvarieties X in tensor space, or typically they are projective varieties, so given by homogeneous polynomials in a default tensor. Okay? But we want to describe these ideals in terms of such gadgets, in such irreducible G modules. Okay, so that's the philosophy. So it's very difficult to calculate these very big prime ideals, or impossible, unless you use the symmetry. So we want to use the symmetry and describe our ideals, generators, conjuncts, syzygies, whatever, in terms of such modules. So that's the name of the game. Okay, that's the name of the game. Now these invariant subvarieties are everywhere. So for example, yesterday afternoon we discussed the variety of 3 by 3 by 3 tensors of rank at most 2. And we agreed that its prime ideal is generated by 20 cubic polynomials that we got as the 3 by 3 minors of a Catallacticant, Hankel, moment matrix, right? That is one of these modules. That's sort of the invariant point of view. Okay? So whenever you have an invariant, that is to say geometric, according to Klein, whenever you have a geometric property, it has such a description. Now, this is also very practical. So, what is Gröbner basis theory? Right? So let's think about why Gröbner basis is so great. Right? Because we have the concept of a monomial. Gröbner bases are so great because we have monomials, and we can order monomials, and we can reduce questions to questions about monomial ideals. Now, what's a monomial? Well, a monomial is an eigenvector with respect to a torus. Right? So if the group, we were looking for, where a torus, C star to the n, then an invariant module is sort of a monomial, or something that's spanned by monomials, and that leads us to the concept of monomial ideals. So monomials and monomial ideals and reducing calculations to monomial ideals, all the joy of Gröbner bases, is the same theory in some sense where G is a torus. We're now extending that to a non-abelian situation, the situation of n by n invertible matrices acting. And then, sort of we have these more complicated things that play the role of monomials. Okay? Key example is tensors of bounded rank. So X is the secant variety sigma r of P of A1 times P of PB2, projective spaces of dimension A-1, B-1, C-1, the projectivizations of our 3 vector spaces here. So this is A by B by C, tensors of border rank at most R. This is the rth secant variety of, let's say, gray variety and an object of great importance in algebraic statistics. Let me wrap up by saying a few words about the Salmon Conjecture. Which stimulated quite a bit of work on these subjects. So this concerns the special case A equals B equals C equals R equals 4. The number 4 is special because it's the cardinality of the set ACGT, the number of nucleotides, the basic building blocks of carbon-based life. Each of us has a genome. That's a long, long, long word over an alphabet with 4 letters. Okay? Relationships among biological taxa, such as organisms, genes, blah, 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 is related in a tree-like fashion, and that is the topic of phylogenetics. So in phylogenetics, we're interested in, say, the tree of life, right? So the tree of life, is some big tree, right? At the beginning is like something, like the dinosaur, and down here is you and me and the fugufish, okay? And there are some other guys in between, okay? So that's the tree of life. And the relationship is at the sequence level. So the relationship is at the level of sequences of length 4. So these relationships are described by probabilities that are 4 by 4 by 4 by 4 by 4 by 4 tensors. So that's why 4 is very important. Now it turns out that the case of 4 factors, so we can sort of assume that the branching is like this, that locally such a big tree looks trivalent. And there's a philosophy that says if we understand the algebraic geometry locally around each inner node, then we can patch things together and understand it globally. Okay? And that's why the 4-4-4 case is very important. So this case is very, very important, where you have sort of 3 leaves out here, and this guy also here has 4 states in one position of our aligned genome. Your genome aligns with my genome somehow, and his genome, and her genome. And in some particular position, 17,245,891, I have an A, C, right? Maybe graph theorists have a C in that position, something, right? So, okay? So that's how it goes, okay? And then to compare that, we want to understand this situation, and that's the Salmon Conjecture. So which states that the variety of 4 by 4 by 4 tensors of rank 4 is cut out by a bunch of equations. State this here. Okay, it's cut out by 1,728 equations of degree 5. It's a theorem now, in this form. And 1,000 equations of degree 6, and you throw in also 8,000 equations of degree 9. 3,000?
The same mistake we made.
Ah, okay.
No, that's 8 and the previous one's 3.
Oh, this is 3. I'm sorry. 3, 8. Okay. Anyway, so a bunch of equations of degree 5, 6, and 9. And so this was proved set theoretically and sort of independently. Friedland and Gross have a paper, and then Bates and Luke Erding another paper that involved some nice numerical computations, and I think it's still open whether they generate the ideal. Right? So there's still some work to be done. But what are these equations? How should I email you these equations? Okay? So you want to use these equations. You want to use these equations for statistical inference. You want to use these equations as a test statistic. Right? So how should you sort of take advantage of this? Well, the quintics, they are S311, S211, S211 plus S, the symmetric version. 311, 211, S211, S2111, S3111. Okay? That's the quintics. That's the part in the decomposition of, that we're looking at here that contributes the quintics, and maybe it's somewhere in my table. Okay? Then degree 6, oh no, this is degree 4. This is degree 5. Degree 6, we have S22, 222, 311, and then 2 more leading to the 3000. And you know the dimensions of each of these spaces by the formula, right? By content and hook length. You can immediately calculate the dimensions of each of these, and you know that the dimensions of these spaces are 1728 and 3000 and 8000. The last one is just a single guy, S333. That's it. No? What am I doing? Oh, there are 3 copies. Okay. Okay. Yes. Tensor. I guess I confused myself. Oh, yeah. Okay. In my notation. Okay. So I kind of dropped, in this notation, I dropped the tensor product. Okay. That's 8000. So this 8000 is 20 times 20 times 20, right? Because each of these guys has dimension 20. Okay? So this is a way of organizing this data. This is it gives you a way of checking whether a large bag of polynomials simultaneously vanishes on the variety or doesn't vanish on the variety. It's sort of like, plays very much the role of monomials in Grobner basis theory. So that's an example. Let me just tell you what the equation of degree 9 is, and perhaps more down to earth way. So let me give you the equation of degree 8. It's kind of nice. It goes back to Volker Strassen, who years ago looked at this when studying the complexity of matrix multiplication. And what you do is you take 3 slices of your tensor. So look at 3 slices out of the 4 slices in any way you want. Right? So okay, so you have your 4 by 4 by 4 Rubik's cube, and you take 3 of the 4 slices in some dimension. You call them A, B, and C, and then you take the entries of A times the adjoint of B times C minus C times the adjoint of B times A, and this gives you polynomials of degree 5. So these are the polynomials of degree 5, right? So A has linear entries, the adjoint, which is the inverse with denominator cleared, has cubic entries, C has linear entries, so each entry of this 4 by 4 matrix is a homogeneous polynomial of degree 5. It's a non-zero polynomial because matrix multiplication is not commutative, and that's doing this for all slices, in all possible ways, gives you this vector space. Okay? My time is up. So this afternoon in room 3435 we have 2 wonderful guest lectures starting at 2 p.m.